Euclid is effectively a space telescope, and it will perform a huge survey of the universe. It will cover more than a third of the sky, and due to the finite speed of light, it will be able to observe the evolution of the universe. So it will perform the most accurate and largest 3D map of the universe. Basically, as a space mission, Euclid will enjoy very stable conditions, and so that means that it will be able to provide a very accurate measurement that will be disturbed very little by what we call systematic effects, like the presence of the atmosphere. And so that will allow it to measure very precisely the small effects that describe the geometry of the universe. And by studying these small effects, we can learn a lot about what is in the universe. In the theory of general relativity, there is a link between the geometry of space-time and what is in the universe. And so to give an example, that was very important historically. About 25 years ago, there were two groups who looked at distances to very bright objects, supernova exploding stars, to measure the expansion history of the universe. And they found out that the expansion is accelerating. And this was very surprising, because normally if you have normal matter in the universe, it is a bit like gravity on Earth. If I throw up a stone, it will fly up into the sky, but it will slow down and eventually it will turn around and fall back down to Earth. And in the same way, the expansion of the universe should slow down over time due to the gravity of the matter inside the universe. But what these two groups observed was that the expansion, even though it had slowed down initially, recently had started to accelerate. And that is a little bit as if you threw a stone into the air and it would slow down, but suddenly it would zip away. And that would certainly be very surprising if you saw that happen. And you would wonder what made this happen. No, a stone would never do that. So something had to be there to make it happen. And in the case of the universe, we don't actually know what this is. It is very puzzling, and we call this dark energy, mostly as a sign of how little we understand it. So one of the goals for Euclid, thanks to its very precise measurements, will be to characterize, space-time very precisely, and therefore to characterize the properties, for example, of this dark energy very precisely. General relativity is extremely well tested on what we call small scales. Small here is the scale of the solar system, which is not exactly small, but for cosmologists it's tiny. But we don't really know what happens on very large scales. And so the Euclid observations will allow us to test gravity on very large scales. And indeed, one of the possibilities that gravity works differently on large scales, and that this then leads to the accelerated expansion of the universe. My favorite outcome is that we observe an expansion rate that is not in agreement with the simplest model for dark energy, which is a cosmological constant. And in addition, we can measure very precisely the spatial curvature and the time distortion, because this would give us a good idea where we have to look to explain dark energy and maybe dark matter.